In enterprise environments where uptime, scalability, and data integrity are non-negotiable, Oracle Database and Oracle RAC remain foundational technologies. In this video, we will break down Oracle Database architecture, memory and process structures, RAC internals, cache fusion, use cases, and architectural trade-offs. Let's begin. Every Oracle Database instance relies on a shared memory region known as the System Global Area, SGA. This is where the core data structures live, and understanding its layout is essential for anyone managing performance or troubleshooting issues at scale. At the heart of the SGA is the database buffer cache. This area holds copies of data blocks read from disk. When a user session queries or updates a table, the relevant blocks are brought into the buffer cache. If those blocks are already present, Oracle avoids a physical read and serves the data directly from memory. The buffer cache is the first line of defense against slow disk access, and it is often the largest SGA component in high-throughput systems. Alongside the buffer cache sits the shared pool. This region contains two critical subcomponents, the library cache and the data dictionary cache. The library cache stores parsed SQL statements and their execution plans, so repeated queries can skip the parsing phase and execute faster. The data dictionary cache holds metadata about database objects, tables, indexes, users, and privileges. The shared pool is also where Oracle manages session information, locks, and cursors, and it is a frequent focus for tuning in complex workloads. The Redo log buffer is another key SGA region. Here, Oracle collects change vectors, records of every modification made to data blocks. When a transaction commits, the log writer process flushes these vectors from the redo buffer to the online redo logs on disk. This mechanism guarantees durability. Once Oracle acknowledges a commit, the corresponding changes are safely stored and recoverable after a crash. Several optional pools round out the SGA. The large pool supports parallel query operations, RMAN backup buffers, and shared server connections, helping to offload memory-intensive activities from the shared pool. The Java pool is reserved for Java code running inside the database. The Streams pool supports Oracle Streams and Golden Gate replication features. Each of these SGA regions serves a distinct purpose. Data blocks, SQL plans, metadata, and change vectors are carefully separated to optimize access patterns and concurrency. This memory structure forms the backbone for Oracle's high-performance transaction processing, and it sets the stage for understanding how background processes interact with these regions to maintain consistency and recoverability. Oracle's background processes form the backbone of memory consistency, each one tied to a specific duty within the System Global Area. The database writer DBWN quietly moves change data blocks, dirty buffers from the buffer cache to disk. It acts when the cache fills, a checkpoint triggers, or memory must be freed, always aiming to minimize random input-output. DBWN's work is about efficiency, not durability. Durability falls to the log writer LGDWR. When a transaction commits, LGDWR flushes all related redo entries from the redo log buffer straight to the online redo log files. Only after this flush does Oracle confirm the commit. This guarantees that every committed change is recoverable, even if the system fails. LGWR may also write if the redo buffer fills before a commit, ensuring no data is left in limbo. The checkpoint process, CKPT, coordinates with both DBWN and LGWR. At each checkpoint, CKPT signals DBWN to write all dirty buffers up to a specific system change number, SCN, and updates file headers with this SCN. This marks the recovery line, telling Oracle where to start applying redo after a crash. System Monitor, SMON, steps in after crashes or shutdowns. SMON applies redo generated since the last checkpoint, rolling forward committed transactions and rolling back incomplete ones. This leaves the database consistent no matter how it was interrupted. Process Monitor, PMON, handles failed user processes. If a session crashes, PMON cleans up locks, frees memory, and releases resources, preventing leaks and lock contention. This is essential cleanup work. For databases with archiving enabled, the Archiver, ARCN, copies full online redo log files to archive destinations. This supports point-in-time recovery and off-site backups, working in parallel with LGWR to ensure no committed redo is lost. A typical transaction flows through these processes. A user updates a row and the change lands in the buffer cache and the redo log buffer. On commit, LGWR writes redo to disk. DBWN later flushes the data block to the data file. And if a crash occurs first, SMON recovers the change using redo logs. Each process links memory edits to durable storage, preserving a consistent view of the data. A commit in Oracle is not just a logical event, it is a physical promise. When a user session issues the SQL command commit, Oracle does not immediately declare success. Instead, every change made during the transaction is first recorded as a change vector in the redo log buffer, a dedicated area of the System Global Area, SGA. The key moment comes when the log writer process, LGWR, steps in. LGWR takes all pending redo entries for the committing transaction and writes them out to the online redo log files on disk. Only after this disk write completes does Oracle acknowledge the commit back to the client. This is the point of persistence. If LGWR cannot flush the redo, the commit is not confirmed, and the user waits. The commit SCN system change number is assigned as part of this process, stamping the transaction with a unique, ever-increasing number that orders it in the global history of the database. The guarantee is absolute. If Oracle returns success, the redo for that transaction is safe on disk, ready to be replayed even if the instance crashes seconds later. The data blocks themselves may still reside in memory, unwritten to disk, but the redo ensures that every committed change can be reconstructed. This strict ordering, redo first, commit acknowledgement second, forms the backbone of Oracle's durability and recovery model. The moment LGWR completes its write, the transaction is considered durable, and the database can move forward confident that no committed data will be lost no matter what happens next. When an Oracle instance crashes, the database enters a delicate phase, restoring consistency without losing any committed data. System monitor process, SMON, takes command of recovery. The process is methodical and precise, unfolding in two main stages: roll forward, then roll back. The roll forward phase begins with SMON reading the redo log files from the point of the last checkpoint. Every change recorded after that checkpoint is reapplied to the data files, block by block. This includes changes from both committed and uncommitted transactions. SMON relies on the sequence of redo records to reconstruct the exact state of the database at the time of failure. The goal is to bring all data files up to the latest possible system change number, SCN, as recorded in the redo stream. Once all redo is applied, the database is physically consistent with every change that happened before the crash. But not all of those changes were committed. Some transactions were in flight, left incomplete by the interruption. Here, the rollback phase begins. SMON uses undo records to reverse any changes from transactions that did not commit. These undo records have been managed automatically since Oracle 9i by Automatic Undo Management, and they provide the before image of each modified row. SMON systematically walks through the list of incomplete transactions, restoring each affected block to its prior state. Only after all uncommitted work is rolled back does Oracle open the database for new activity. The process is invisible to users, but it guarantees that no committed transaction is lost and no partial change pollutes the data. This ordered replay, redo first, then undo, forms the foundation of Oracle's crash recovery algorithm, ensuring the database always returns to a clean, reliable state after any failure. Oracle Real Application Clusters operate on a foundation of tightly integrated cluster components, each responsible for keeping multiple database nodes synchronized and resilient. At the center is the Oracle Cluster Registry, OCR. This shared repository holds all cluster configuration data, node membership, resource assignments, and failover rules. Every node in the cluster reads from the OCR at startup to confirm its identity and learn about other nodes. The OCR is mirrored across multiple devices, ensuring that even if one copy fails, the cluster remains operational. Voting disks work alongside the OCR to prevent split-brain scenarios. Each node regularly writes a heartbeat to these disks, affirming its presence in the cluster. If a node stops responding or loses access to the majority of voting disks, it is automatically fenced off, protecting the integrity of the data files. Oracle recommends at least 3 voting disks for redundancy, and the cluster requires a strict majority to stay online. This quorum model ensures that only one partition of the cluster can access shared storage at any time. Cluster synchronization services, CSS, orchestrate node membership and heartbeat monitoring. CSS daemons exchange messages over the private interconnect and update voting disks every second. On startup, CSS reads both the OCR and voting disks, then coordinates with other nodes to elect a cluster master. If a node misses heartbeats, CSS triggers eviction within seconds, minimizing the risk of data corruption. For client connectivity, single client access name or SCAN, listeners provide a single network endpoint that abstracts the complexity of multiple nodes. SCAN listeners register with local listeners and balance connections across the cluster. If a node fails, SCAN automatically redirects new sessions to surviving nodes, supporting high availability without manual intervention. And together, these components define the physical and logical canvas for Oracle RAC. Shared data files, mirrored OCR, and quorum enforced voting disks ensure that every node starts with a consistent view of the cluster, while CSS and SCAN listeners maintain seamless operation as nodes come and go. Cache Fusion transforms how Oracle RAC instances coordinate access to shared data blocks, replacing the old model of physical disk handoff with direct memory-to-memory transfer. At the center of this process, the Global Cache Service, GCS, tracks which instance holds each block and in what state. States are not simply binary. A block can be held in exclusive mode, allowing updates, or in shared mode for read-only access. These modes form the basis of a state machine that governs every block's journey across the cluster. When a session on one node needs to modify a block that is currently held in shared mode by another node, it triggers a precise protocol. The requesting instance's Lock Manager Server, LMS, sends a request to the GCS for exclusive access. The GCS consults its global resource directory, pinpoints the current holder, and issues a downgrade message. The holder's LMS process responds by serializing the block, capturing its most recent state, and downgrading its own access to null. The block, now frozen and ready for transfer, is sent directly over the cluster interconnect as a Cache Fusion buffer, typically an 8 kilobyte payload. The receiving instance installs the block in its buffer cache in exclusive mode, ready for updates. The GCS records the new ownership, and if any other nodes hold past images for recovery, those are tracked as well. Transitions from shared to exclusive and from exclusive to shared happen in microseconds with the GCS and Global In-Queue Service, GES, ensuring that only one node can ever update a block at a time. This protocol eliminates the need for disk-based handoff, keeping latency low and throughput high. In practice, the handoff is visible in diagnostic views like $GC_ELEMENT, where state transitions such as SL0, shared local, to XL0, exclusive local, can be traced in real time. Each message, request, grant, transfer, and acknowledgement forms a tightly orchestrated sequence, ensuring data consistency and rapid failover across the cluster. Oracle RAC exposes its most telling performance signals through wait events, diagnostic breadcrumbs that reveal where time is spent and where contention builds. In an ERAC environment, the most critical of these are the Global Cache Wait Events, abbreviated GC. These events appear in active session history and AWR reports with names like Global Cache Current Block Busy, Global Cache Consistent Read Block Busy, and Global Cache Buffer Busy. Each points to a specific phase of Cache Fusion, requesting a block for modification, waiting for a consistent read copy, or being stalled by another instance holding a needed block. The Global Cache Current family of waits tracks delays when an instance needs the latest version of a block for an update, but another node has it locked. Global Cache Consistent Read Waits arise when a session requests a read consistent version, a snapshot as of a particular system change number, but the block must be built and shipped from another instance. Both types are visible in real time through the $V session and $V system event views, and their presence in the top event section of an AWR report signals that block transfer over the interconnect is a measurable cost. SRE teams often sum it up in a single line. If GC waits climb the chart, you are paying the remote block tax. These waits do not just flag latency, they quantify the impact of cross-node block sharing. The taxonomy of global cache wait events, current, consistent read, and buffer busy offers a direct lens into how well the cluster's interconnect and workload partitioning are holding up under load. Diagnosing these events is the first step toward deciding whether to tune, redesign, or even reconsider the RAC approach for a given workload. When a node in an Oracle RAC cluster fails, the system responds with a choreography designed for uptime. Surviving nodes detect the loss within seconds, thanks to constant heartbeats exchanged over the cluster interconnect and written to voting disks. Cluster synchronization services immediately evicts the failed node, fencing it off to protect data integrity. Sessions connected to the downed node are not simply dropped. Oracle's fast application notification and transparent application. Failover mechanisms trigger, redirecting new connections to healthy nodes. In-flight transactions may be rolled back, but active sessions can reconnect automatically, often without manual intervention. Planned maintenance, such as patching, demonstrates another strength. Oracle RAC supports rolling patches, allowing administrators to take one node offline, apply updates, and return it to service before moving to the next. The database remains available throughout, with client sessions rerouted in real time. Cleanup operations run in parallel, minimizing the window of reduced capacity. This approach means patching can be completed without a full outage and without risking data loss or corruption. By combining rapid failure detection, automatic session redirection, and rolling maintenance, Oracle RAC delivers a level of availability that stands out in enterprise environments where downtime is measured in lost revenue and trust. Deciding whether Oracle RAC is the right fit comes down to hard numbers and business realities. For mission-critical workloads, every minute of downtime can mean thousands or even millions lost. Gartner's latest figures put the average cost of downtime for banks at over $9,000 per minute, while telecom and high-frequency trading firms often report even higher stakes. In these environments, Oracle RAC's promise of continuous availability is not just a luxury, it is a requirement. Performance metrics set the next line in the sand. RAC only delivers when the cluster interconnect keeps one-way latency below 25 to 50 microseconds, and when global cache waits, those GC events tracked in AWR, stay under 10% of total database time. Anything higher and the remote block tax starts to erode the benefits of clustering. A bank DBA recalls that we ran AWR during peak hours. If GC weights crossed 8%, we knew we had to revisit partitioning or network tuning. Industry cases echo this threshold. In banking, RAC supports core transaction processing where planned outages are unacceptable, and partitioned account ranges keep GC weights low. High-frequency trading platforms demand under 10 microsecond interconnects, with engineers running synthetic failover drills to validate that GC weights never break the 10% ceiling. Telecom billing systems, after migrating to RAC and partitioning workloads by customer region, saw GC weights drop from 18% to under 4%, unlocking higher throughput and safer bill runs. Alternatives like Oracle Data Guard offer robust disaster recovery, but cannot match RAC's active uptime or rolling patching. The decision hinges on real metrics, cost of downtime, interconnect latency, and measured GC weights. When these numbers align, RAC is not just justified, it is essential. Today, every mission-critical system rides on the invisible logic of database internals. As cloud deployments surge and downtime costs spiral, nearing $5,600 per minute in 2024, architecture choices demand more scrutiny than ever. The complexity beneath Oracle's surface is not just technical, it is strategic. In this landscape, understanding is not optional, it is what keeps the world running. Share your perspective below.